Hello, I am Ashadul Adalder, a research scholar from Ramakrishna Mission Vidyamandira, Belur Math, India. I have worked with several one-dimensional nanomaterial and composite material, 2D graphene-based nanomaterial, etc. along with their several application, mainly in electrochemical application. In this presentation, I will limit my discussion to mix 1D 2D nanomaterials and also use it in a electrochemical application. And my presentation topic is investigating manganese phthalocyanine graphene based heterostructure for the electrochemical production of ammonia. So why ammonia? Because ammonia is a essential raw material to use like leather industry, rubber industry, food and beverage industry, mining industry, petroleum industry, and mostly the important agricultural based industry. Scientist Mill, in his famous Nature article, tells the greatest invention in the 20th century was that the establishment of the Haber-Bosch process. Then why the Haber-Bosch process is the greatest invention in 20th century? Because in 19th century, without Haber-Bosch process, the world population is near about 1.8 billion. But by the blessing of the Haber-Bosch process, the world population is near about 7.2 billion. Hence, it is the greatest invention in the 20th century. Now the question will come, how the ammonia is produced or was produced during the Haber-Bosch process. So in Haber-Bosch process, the essential raw material, first hydrogen produced from the methane, then the produced hydrogen reacts with nitrogen in presence of iron catalysis with a high temperature like 4 to 500 degree temperature and high pressure like 200 atm pressure, and it produces ammonia. So the Haber-Bosch process actually consume lot of energy. So it consume over 2% of energy as well as emits lot of carbon dioxide emission. So it emits world 1.8% of total greenhouse gas. So from the economical sustainable point of view, one must think a process which can alter the Haber-Bosch process. So if you think the Haber-Bosch process is the generation 1, then the next generation comes which is the generation 2, that is the indirect electrochemical route. So in indirect electrochemical route, first the hydrogen, where in case of Haber-Bosch process is produced from methane. So in case of generation 2, hydrogen is produced from the HER process. After that, the produced hydrogens react with nitrogen and it convert to ammonia. Now we are focusing on the third generation process, which is the direct electrochemical route. So in direct electrochemical route, nitrogen or nitrate, these two are easily available in our nature. So these two can convert it to ammonia direct electrochemical route. And in this process, it does not require any high temperature or pressure. So coming to the nitrogen to ammonia process, that is called nitrogen reduction to ammonia. That is also we can call NRR process. So in electrochemical NRR process, the nitrogen in presence of a catalyst and a suitable electrochemical chamber or electrolyte, it produces ammonia. But the question is that we all know nitrogen is a inert molecule. So breaking the N triple bond end, it's required 942 kilojoule per mole of energy. Also, it is less soluble in aqueous medium. So the production of ammonia is very less. So the next thing will come where we can alter that the nitrogen molecule. Now the second compound nitrate comes in our mind, Also, we know the nitrate is a pollutant, so consume lot of nitrate, it can cause a blue baby syndrome disease. And in case of solubility, nitrate is easily soluble in aqueous medium, and the bond breaking energy for an NO bond, it is near about 240 204 kilojoule per mole. So that is quite less than that of N triple bond. Also, nitrate, in case of nitrates, it has a low energy barrier to produce ammonia, but in case of nitrogen, it has a high energy barrier. So thinking about this, the scientists are focusing to convert nitrate to ammonia by the direct electrochemical route. So for that purpose, one must choose a suitable electrocatalyst that can easily convert nitrate to ammonia. So one must choose a catalyst which has a highly stability, activity, selectivity, recyclability. And in our case, by seeing the nature chlorophyll-like structure, we choose metal phthalocyanine based electrocatalyst which has a central metal and four adjacent nitrogen atom. And in our case, we first focus MNPC, that is manganese phthalocyanine. And why we choose manganese? Because it has a D5 system, so 5 ampere electron is present. So manganese phthalocyanine can synthesized by a solvothermal technique by using a chemical precursor of manganese acetate, thalonitrile, ethylene glycol, and the condition was maintained 180 degrees centigrade for 24-hour experiment. And next, we mixed manganese phthalocyanine with a RGO system. So RGO was produced, that is RGO mean reduced graphene oxide. It can produce by the modified Hummer method. So starting from graphite, first we oxidize by KMnO4 to produce graphene oxide. Then further we reduce to produce reduced graphene oxide by hydrogen hydrate, by using hydrogen hydrate. Then why we use, or what is the advantage of reduced graphene oxide? Firstly, RGO provide an active support and enhance the electron mobility in the MNPC RGO system. Secondly, it prevent the manganese phthalocyanine or MNPC from agglomeration, which is a very important as a catalytic process. And thirdly, in RGO addition in the catalytic system, increase the non-metallic constituent, which can turn the main competitive reaction during the ammonia production, that is HER, which can suppress the HER process. And lastly, RGO incorporation play a key role to increase the exposed active site, which further enhance the nitrate production. So this is the first we produce RGO system, then MNPC and RGO, we make the MNPC RGO system. After that after that our synthesized MNPC, we did several characterization technique like X30, and from ICDD card value we match these planes and it confirmed that it is produce of MNPC system. And then we check XPS and it confirms the MNPC in 2+ state. Further we confirm the oxidation state of the Mn in MNPC by the Janissy experiment, and we also check several morphological characterization by APCM or TEM analysis, and elemental mapping confirm that the presence of Mn, carbon and nitrogen element in the MNPC RGO system. After several characterization technique, we further focus on our electrochemical application purpose. So before going or in electrochemical application, first we design an H type cell where here the cathode chamber and anode chamber are separated by a junction that is called a napkin membrane. This is a proton, it can only transfer proton from one chamber to another chamber. And in our case, we use nitrate and a sodium sulfate as a electrolyte. And the mechanism from the nitrate to ammonia conversion is like, first nitrate diffuse to the catalyst surface. In our case, as we already tell, in our case we use a catalyst that is MnPC RGO. So first nitrate diffuse and adsorb on the catalyst that is MnPC RGO surface. Then the nitrate system is reoriented on the catalyst surface. Then after then every all electrochemical reaction or happen, that is nitrate to ammonia conversion was happened. Then the final product ammonia dissolved from the catalyst surface, then it diffuse to the electrolyte medium. So this is the overall mechanism for nitrate to ammonia conversion via electrochemical route. Now, as I already tell, the one must choose a electrocatalyst which is a highly activity, stability, recyclability, and selectivity. So coming to the first activity purpose. So in our case, there is a lot of active site, that is metal center, carbon center, nitrogen center. So from theoretical calculation, it's confirmed that the only metal center will play a key role to convert nitrate to ammonia. So in our case, we have two options. One is MNPC only, and second is MNPC RGO system. So it shows that the MNPC RGO system has a better option or less gives free energy to convert nitrate to ammonia. Next, the stability term. In our case, we saw the our catalyst is stable up to 50 hours. And coming to the selectivity purpose. So during conversion from nitrate to ammonia, there is a chance to produce several byproducts like hydrogen or hydrogen. But in our case, we check the hydrogen with a standard calibration of hydrogen. In standard hydrogen calibration, it shows a peak like 450 nanometer range. But in our cases, we did not see any kind of signature peak of hydrogen in 450 nanometer range. So we can conclude that our catalyst is suitable for this selective reduction of nitrate to ammonia. And for catalyst real life application, one must think about the recyclability of the catalysis. And in our cases, we we see that the ammonia production rate or real rate or ammonia Faradic efficiency is near about almost constant up to 10 cycle. So we can conclude that our catalyst is the highly recyclability. Now come to the what is the exact mechanism during the nitrate to ammonia production. From the theoretical calculation or we can say DFT calculation, we can see nitrate to ammonia conversion is a direct. It shows the 8 electron transfer process. So in our cases, we have a MNPC system and we have a MNPC RGO system. So here we can see that the MNPC RGO system has a less free energy compared to the MNPC system. Also, in path determinant step is very less or less compared to the MNPC system. So So we can tell that the MNPC RGO system is a better conversion of nitrate to ammonia. We also calculate the ammonia, because in our cases the actually production of nitrate to ammonia, it will stay in liquid medium, that is a cathode chamber of our system. So we must quantify the ammonia produced in the electrolyte medium. So to calculate the actual amount of ammonia present in the electrolyte solution, first we, we prepare a standard calibration curve of ammonia by using a standard ammonium chloride solution, and after that, from the standard calibration, we calculate the produced ammonia during nitrate reduction by a well established independent blue method test. And using independent blue method test, we produce a independent blue color, and we use that independent solution in a UV chamber, and via UV we get a signature peak of ammonia. After that, we calculate the ammonia yielded by this equation, where C of C is C is indicate the concentration of ammonia after the nitrate reduction, and V is the volume of electrolyte used during the reduction process, and T is the time of reduction, and M is the mass of catalyst loaded on the working electrode. And we also calculate the Faraday efficiency by this equation. And here in our cases, we check several conditions in piston phthalocyanine system, in RGO only MNPC system, and in our cases we loaded MNPC RGO on a carbon paper. So we have also checked the carbon paper, how much ammonia can produce from the carbon paper, and several ratio of MNPC RGO system. And we also check the open circuit potential also. So in case open circuit potential or without nitrate solution present in the electrolyte solution, we did not see any kind of signature peak of ammonia. But in case of MNPC RGO system, we get a signature peak of ammonia, and the value is getting 20k microgram per hour per milligram catalyst. And in our cases, we can see our catalysis can convert nitrate to ammonia with a Faraday efficiency nearly 100%. So from here, I can conclude our catalysis, that is MNPC RGO system, has a highly activity, stability, recyclability towards the nitrate to ammonia conversion. And this work is published in SS Catalysis Journal in 2023, and this work also published or select as a cover in SS Catalysis Journal. And I would like to acknowledge my guide, Dr. Uttam Kumar Puroy, my family, my labmate, and ACRB for providing the research grant during my research work. And thank you. And lastly, thank you Science Father, Fiberreinforced Polymer, International Research Award on Fiberreinforced Polymer. So thank you. Hope you all enjoy my presentation. Thank you.